Complex numbers are numbers that can be represented in the form a plus bi, where a and b are real numbers, and where I is the imaginary section, which is defined as the square root of -1. The objective of this video is to understand the basic operations of complex numbers, such as the sums, products, and quotients, as well as the conjugate and division of complex numbers in the Cartesian form a plus bi. The second objective of this video is to understand that complex numbers can be represented geometrically on the Argand diagram, where the real part of the complex number is on the x-axis and the imaginary part is on the y-axis.
In Cartesian form, addition and subtraction are fairly simple. You group the real components together and the imaginary components together like so. Here's an example for addition. Let's look at it on the Argand diagram. Here on the Argand diagram, the x-axis represents the real portion of the complex number while the y-axis represents the imaginary. You can see that the x components add up together and the y components add up together to form the sum. Now here's an example of subtraction. Similarly, you group the real components together and the imaginary components together. On the Argand diagram, you can see that the x component and y component of the end result is the same as the difference between the two numbers. And now, multiplication. Algebraically, products of complex numbers in the Cartesian form is the same as multiplying any two terms with another two terms, like this, where a plus bi is a complex number and c plus di is another complex number. One thing to be noticed, of course, is that I times I is equal to -1. Here is an example. Now let's look at it geometrically. If we plot the previous example on the plane, it'll look something like this. Looking at this example, can you see how the two numbers and the product are related? Well, firstly, if you add up the angles of the two complex numbers like I'm doing here, you'll find that you get the angle of the product. Now let's look at the magnitude. You can find the magnitude of a complex number by using the Pythagorean theorem. And as you can see here, if you multiply the two magnitudes, you get the magnitude of their product. So, geometrically, the product of two complex numbers is the product of their magnitude and the sum of their angle. Now let's look at this problem. In a polynomial with complex roots but all real coefficients, how would the complex root multiply out into the real coefficients? In other words, what would you multiply a complex number by to get a purely real number? The answer is conjugates. If a complex number is in the form a plus bi, then its conjugate can be expressed as a minus bi. As we found before, multiplication with complex numbers is, geometrically, multiplying its magnitude and adding its angle. A conjugate of a complex number has the negative angle of the complex number, so when multiplied together, it'll end up as a purely real.
Moving on to the quotients of complex numbers. Here's how you do it algebraically. First, you have a plus bi over c plus di. You can use the complex conjugate of the divisor, which is c minus di, to make the divisor a purely real number by multiplying it together. That way, it can then be shown in the form a plus bi, the Cartesian form, where a and b are real numbers. Here's how you do it by steps. First, you go a plus bi over c plus di times c minus di over c minus di, which then you can expand it into bracket ac plus db bracket plus cb minus dai over c squared plus d squared, which then you can make it into two fractions, ac plus bd over c squared plus d squared plus cb minus da over c squared plus d squared I. Now here's a question for you to solve to try to see how this actually works. You can pause if you want to try first, and then the answer will be revealed soon. Here's the solution for the question 1 plus 3i times a plus bi equals 5 plus 5i, solve for ab. So first you can rearrange the equation into a plus bi equals 5 plus 5i over 1 plus 3i. Now you can see you can times the divisor by its conjugates, which you times 5 plus 5i over 1 plus 3i by 1 minus 3i over 1 minus 3i, which then you can simplify it into 5 minus 15i plus 5i plus 15 over 1 plus 9, which then if you simplify, you'll see it's 20 minus 10i over 10, which equals to 2 minus I, which then you can see a equals to 2 and b equals to negative 1.